Hello. So, as mentioned, my name is Ben Dowling, and I'm a student at the Queensland University of Technology under the supervision of Douglas Stebila, who has recently moved to McMaster University. This work was done on securing the authentication of the network time protocol, and was partly done while I was a Microsoft research intern under the mentorship of Greg Zaverucha, who is also one of our co-authors. So as a little bit of an overview for the talk, first we'll begin with an introduction of time synchronization protocols in general and add some background on the network time protocol itself. We'll introduce our new construction for securing the authentication of NTP, which we entitle ANTP. We describe our novel security framework for analyzing time synchronization protocols, its goals, and we touch on our security analysis of ANTP. We finish by talking about our proof of concept implementation and the experiments we performed and the results we saw. So let's get started. So why is it so important to know the time? So in recent years, we've seen man-in-the-middle attacks on the network time protocol that allow rollback style attacks on time synchronization. Now, I'm assuming we're all familiar with X509 certificates, and we're aware that each has an associated validity period. Now, if you consider an adversary that's able to set your clock back to 1995, if your bank has leaked its private key in the years since then, or the adversary has spent 20 years working on cracking the key pair, the adversary may be able to man-in-the-middle TLS connections by injecting old certificates that you still think are valid. Kerberos is another example. It requires strict 5-minute synchronization with the communicating party, and so an adversary, if they're able to shift your time, is able to cause denial of service attacks against Kerberos. Similarly, HSTS has validity periods associated with the policies, and so an adversary capable of shifting your time is able to jeopardize the security of your connections. We've got there an example of a X509 certificate from QUT, and we can see that it has an associated validity period that expires on the 30th of November. So a little bit of history on the network time protocol. The most popular time synchronization protocol is the network time protocol, introduced in '85 by David Mills, and revised several times, as we can see. In its most used mode, which is client-server mode, the client pings the server periodically with their current time and attempts to compute the offset between the two machines and adjust their time appropriately. However, NTP v3, which we see was introduced in '92, was the first variant of NTP that actually started utilizing authentication. And in this case, it's pre-shared key authentication by using an MD5 keyed hash. Before this point, any man-in-the-middle could easily modify the timestamps included by the server and force the client to incorrectly synchronize the time. And indeed, the establishment of these pre-shared keys is considered out of band for NTP. So even if you want to try and get secure authentication of your time synchronizations from a time server run by NIST, you have to set up snail mail or fax in order to get the pre-shared key, which is real state-of-the-art cryptography. So in 2010, we see NTP version 4, which introduces AutoKey, which is a PKI-based authentication mechanism. Now, subsequent analysis of AutoKey has shown it to be dangerously broken. There's identity schemes that have been introduced that can easily be overridden. In addition, it has a trusted certificate self-sign setup that is trivial for an adversary to force a client to utilize. So it's not quite that great. Now in 2013, essentially an evolution of AutoKey was introduced, which is the Network Time Security Protocol. And it inherits a lot of design features, including PKI-based authentication, but we'll elaborate a little bit more on that in a little while. But to go into a little bit more detail into NTP as its mainstream use today, we'll go through the protocol flow. So we'll notice that the client starts by accessing its own time and creating an NTP message with this timestamp, and eventually pinging the server with this NTP request. Immediately upon receiving the request message, the server records the current time as the T2 timestamp, and then at some future point will access its clock and generates a new timestamp T3. The server creates an NTP response message, which is T1 concatenated T2 concatenated T3, and sends it without delay to the client. So the client records the time upon receiving the response message and uses the 4 timestamps to determine the latency time, approximate the propagation time, and compute the offset between the 2 machines as such. So the client determines the total round trip delay by taking the difference of the total round trip that it's seen minus the server processing time between T3 and T2. The client approximates the propagation time by halving this value. So it implicitly assumes symmetric delay. The offset is then computed as the difference of the server transmit timestamp T3 with the client receive timestamp T4 with the addition of the offset. And it's fairly intuitive to see that if the adversary doesn't have the power to modify the timestamps in transit, then the only way that they can influence the clock update function for the client is by delaying the messages asymmetrically. And we can bound the amount of error that the adversary can introduce via this mechanism by the total round trip time between T1 and T4. We can also see that, So it's pretty obvious that the lack of authentication in timestamps is an objectively bad thing, as it allows the adversary to inject their own bad timestamps and force inaccurate time synchronization. And we note that a man in the middle can also attempt to delay and advance packets in order to add and remove propagation error. So what should a security protocol tasked with securing NTP be able to do? So the first few goals are fairly self-evident. We want to be able to authenticate messages from the server. We want to be able to protect against modification of the messages in transit. We want to be able to protect in some way against replay and delay attacks. But since we're working with time synchronization services, there are a few additional restrictions on our protocol to construction. First, any cryptographic protection of the server messages introduces an asymmetric delay and thus introduces error into the approximation of the propagation time, which directly affects the offset and introduces error into the clock update function. So we require any protections cryptographically to be at as little computation time as possible, or even attempt to find a way around introducing delays in this manner. The next two are more practical concerns. So there are, I think, about 600 primary time synchronization servers out there at the moment. So those are servers that are connected to a timekeeping device, such as an atomic clock. But there are millions, if not billions, of clients out there who are all attempting to access and synchronize their times with these servers. So any kind of state that is required to be maintained by the server immediately makes the construction a lot less scalable. And the same goes for computational load. But I mean, why do we need another protocol? I mean, we already talked about NTS, network time security, that already exists. But I mean, what else? Why can't we establish like a TLS connection in order to authenticate and protect the sending of NTP messages, or even use Applebaum's TLSdate in order to fetch time synchronization requests? Well, using TLS has its problems. It can't fully support a stateless server between the initial handshakes, and requires a server to maintain mappings between clients and sessions. So again, it's making our construction less scalable. It also adds asymmetric cryptographic delay, both of which we want to do without. TLSdate uses timestamps included in the hello messages of the TLS handshake, which doesn't allow the client to account for the server processing time. So for instance, fetching certificates or generating Diffie-Hellman values, things along those lines, which is what the T2 and T3 inside the standard NTP protocol allows us to do. And it also adds cryptographic delay to the time synchronization data. And in addition, once TLS 1.3 eventually comes into fashion, TLS 1.3, it's currently in draft status, and it's considering removing the timestamps inside these hello messages. But that'll be like 15 years away. Okay, what about network security? I mean, it was designed to fix the problems in AutoKey, and it's designed to be an authentication protocol for time synchronization protocols. So it should be pretty good. And it is pretty good. But there's definitely room for improvement. As we'll see on the next slide, it inherits a lot of the design decisions from AutoKey, which requires clients to manage and maintain their own public keys and certificates. It doesn't allow for parties to remove cryptographic delay, and it's unnecessarily expensive on the server side in terms of public key operations. And in addition, when we initially analyzed the the network time security protocol, when we were first writing this up, there was also downgrade style attacks on the negotiation of cryptographic primitives. So getting a little bit ahead of ourselves at this point, but here is a comparison to sell our point. So we noticed that NTS and AutoKey require 4 round trips to establish time synchronization. Now, each of these protocols, and that includes our own ANTP, has an initial few rounds, so 3 in the case of AutoKey and NTS, and 2 in the case of ANTP, to establish a shared secret key. And then it utilizes that shared secret key in subsequent time synchronization phases. We note that NTS servers require 3 public key operations and 2 symmetric key operations in order to establish this shared secret key. And then additionally, 2 symmetric key operations during every preceding time synchronization phase. In comparison to our construction, which will only require a single public key operation with, admittedly, 6 symmetric key operations in order to establish that shared secret key, and 2 symmetric key operations in order to establish time synchronization. So, heading into our construction now, it's split up into 3 separate phases: a negotiation phase where a client and a server negotiate cryptographic primitives, and the server is able to offload server state. A key exchange phase where, as the name suggests, the client and the server is able to establish a shared symmetric key, which the server again is able to offload onto the client. And end time synchronization phases, where you utilize the same shared symmetric key in order to protect NTP requests and responses. So we'll have a look through our protocol. So we begin with our negotiation phase. The client generates a nonce and sends the nonce and the list of supported algorithms to the server, which negotiates the optimal set of cryptographic primitives. The server then creates a hash of the message 1 from the client, as well as its own supported set of algorithms and its own certificate information. It encrypts this data under its long-term secret key S, which is a pseudo session ticket idea used from TLS in order to offload server state maintenance to the client. So the server sends over M2, which is the concatenation of its algorithms, its certificate information, and the opaque value that contains this hash. Now we get to the key exchange phase, where the client first negotiates the optimal set of cryptographic algorithms. It also generates the same hash value, and then uses the negotiated key encapsulation mechanism in order to generate a ciphertext and a pre-master secret. Sending across the opaque value that was sent across in the negotiation phase, along with this ciphertext, the server decrypts the opaque value and also generates the pre-master secret based on decapsulation of the ciphertext. And the server uses the pre-master secret as input to the KDF in order to generate the session key, and then utilizes, again in a session ticket fashion, an encryption of a second opaque value. Finally, the server uses the session key to generate a MAC over the hash value concatenated with the client's M3 message and concatenated with its second opaque value, which the server promptly sends to the client. The client verifies the MAC, authenticating both the negotiation phase and the key exchange phase. So this is the actual time synchronization phase, meant to reuse the session key in order to authenticate time synchronization data. The client generates a new nonce and also performs a standard NTP computation, as we saw before. Sends over the NTP message concatenated with this new nonce and the second server opaque value. Again, as in standard NTP, the server takes note of the time of receipt of this message and then decrypts the opaque value in order to find the shared symmetric key. The server finishes the time synchronization data necessary for NTP and computes the MAC over the client message as well as its own NTP response message, sending that to the client. And then the client, from that point onwards, again, time of receipt, and then computes the round trip time, verifies the MAC, and synchronizes the data as long as the round trip time doesn't exceed some accuracy margin, and also that the MAC verifies correctly. Now, we said before that we wanted the ability to potentially remove asymmetric delay caused by cryptographic operations. Now, in order to do so, we allow the sender to immediately send the NTP response message, M6, before authenticating it via the MAC. The client receiving the M6 message without the authentication tag takes note of the T4, the time that it receives it, so you gain back that cryptographic delay, but then waits to receive the second message, M6, which contains the NTP message concatenated with the tag in order to verify that this is correct. So now we'll hit upon our security framework that we use to analyze ANTP, and we will also have a quick, brief look at the proof. So we design a novel security model for time synchronization protocols. It's very similar to BR-style key exchange protocols, has the same ideas. You've got a game played between an adversary and a challenger. The adversary has access to fairly standard BR-style queries, such as create, send, reveal, corrupt. But it has several extensions in order to capture time synchronization protocols. So sessions in their session state also have a time counter. The adversary wins if it can force the client to synchronize time inaccurately, outside the accuracy margin of some server sessions counter. In addition, we give the adversary access to a tick function, which allows it to increment the time counters of any given session, essentially giving them control over the computation speed and latency of a network. However, this is a little bit too strong. Now, one can imagine an adversary that immediately after the server sends over its final NTP message, just ticks over the server until eventually you get to the end and the client is well outside the accuracy margin of the server's time counter. In order to prevent this in the proof, and as well as to capture the notion that clock drift during protocol execution is fairly negligible, we require that the adversary cannot issue tick counters asymmetrically when two sessions have a matching transcript. Note that an adversary between different executions of time synchronization phases can cause clock drift as much as they want. That's allowed within our model. So we prove ANTP secure in both the initial time synchronization phase and subsequent time synchronization phases, bound by the standard assumptions of security of cryptographic primitives, where E here is represented again as an accuracy margin, which we tend to define as the total round trip time. So now moving on to our implementation of ANTP and the subsequent experiments that we do with this. So we utilize OpenNTPD and we extend it using OpenSSL's cryptographic libraries. We give here the cryptographic primitives that we use to implement ANTP. In particular, we implement two different key encapsulation functionalities, RSA PKCS, and static ephemeral elliptic curve Diffie-Hellman in order to compare performance. So what kind of experiments did we do? Well, what we wanted ultimately was to determine the reduction in throughput of using ANTP as opposed to using straight NTP. But we also wanted to determine what additional latency is added and thus what kind of additional error is added due to cryptographic operations. So we had two main experiments. One was a setup at QUT, two client machines connected to a server machine via a gigabit LAN. And we also had two Amazon Web Service instances set up on the East Coast and West Coast in order to see what kind of latencies would be observed in a real-world deployment. And here are our experimental results. I won't go through all the details here, but the most salient comparison is the throughput of the time synchronization phase of ANTP versus standard NTP. So you can see in the first column, the throughput is measured in messages per second, and we can see that typically ANTP could handle on our server machines about 175K messages per second versus NTP, which gives us about 291K messages per second, which we argue isn't significant enough to preclude deployment of ANTP. Now, we mentioned earlier that the time synchronization phase is meant to be done many times. So the negotiation and key exchange phase is performed once, and then you do n times time synchronization phases. So the majority of traffic going to an ANTP server would be time synchronization messages. So that is the most important comparison to be made. In addition, we see here that the latency addition by authenticating the NTP messages is about 21 microseconds. So when you consider approximation of propagation error as about half of the total round-trip time, you're adding approximately an error of about 10 microseconds, which we argue is probably accurate for most clients. Probably accurate enough for most clients. If you wanted to utilize something that is a little bit better, I think you would try and utilize the precision time protocol instead. So here are our results for our experiments on the East Coast and West Coast. And we see here that the latency has now increased from a measurement of microseconds to a measurement of milliseconds. And in particular, what we're seeing is that the impact of synchronization on latency is negligible compared to the latency caused by distance, which we further argue makes ANTP a suitable candidate for securing NTP. So, in summary, we introduce our new construction, ANTP, an authentication protocol that is built over the top of the network time protocol. We formalized notions of time synchronization protocols in a security framework, and we used that security framework to prove ANTP under standard assumptions. We developed a proof of concept implementation of ANTP, and we further evaluated latency and slowdown that is introduced by our construction. So a little bit of future work. One of the things that we encountered upon our analysis was a so-called first boot problem. So it's kind of a chicken and egg problem, right? We're trying to utilize PKI, which itself relies on a validity period in order to correctly find out what the time is. So how do you kind of solve that problem? One of the solutions that we ended up describing was OCSP with nonces to ensure freshness of responses. But I think that we can possibly do better, and it's probably worth investigating. In addition, I feel like there should be a little bit of a caveat on the proof of concept implementation. The PKI-based stuff is a little underdeveloped, and so you can find in our paper the link to the GitHub, which will contain the code for ANTP, and you can have a look and have a play yourself. So thank you. Any questions?
Hi, Kenny Patterson from Royal Holloway. Can you say anything about the status of your source code for this system that you're building?
Sorry, I couldn't quite hear that.
Can you say about the availability of your code?
All right, so it's not quite available at the moment. It will be eventually, probably in the next week or so, uploaded to GitHub on my account. I don't have the link up here, unfortunately, but it's Dowling BJ is the my account name, and you can find the repository in there.
Okay, that's great. And one more comment to your PS. Yes. So come talk to me.
All right, sounds good. Thank you, Kenny.
Okay, do we have any other questions? Okay, then I have one. NTP is a UDP-based protocol.
Yes, it is.
And so it's notoriously vulnerable to either DNS or DDoS attacks of some sort. So did you do any analysis to see if your modifications to the protocol enable either computational or reflectional amplification DDoS attacks?
Yeah, so I mean, adding any type of cryptographic operations to something like ANTP is going to increase the ability of the adversary to cause DDoS attacks. It's an unfortunate side effect, and it's not something that we attempt to address within our work. But it is something that needs to be considered when considering full-time deployment.
Okay, any other questions? All right, let's thank our speaker, Ben.